Hi, welcome to ERC Tipsnology. In this episode, I will be showing you the NPN BJT as an amplifier using the common emitter configuration. First, let's have a review of what a transistor is. In these pictures or figures, you will see this is the PN junction, or this is the P-type and the N-type together. And this will be the anode and the cathode. So this clearly represents the diode. On the other hand, we have here N-type, P-type together, and this is the cathode and the anode. It's the same, it's just reversed. So we have the cathode as N-type and the anode as P-type. Now, what if we put together the N-type, P-type, and N-type? So it will look like this. It's like two back-to-back diodes, which has N-type, P-type, another P-type, and N-type. Therefore, it looks like the NPN. On the other hand, if we put together P-type and N-type and another diode, but back-to-back now, this time is the cathode, N-type, P-type, then it's like we have P and P. So these two are the diode equivalents of the NPN transistor, and this is the diode equivalent of a PNP transistor. Now on this side, we have here the symbol for our BJT. This is the NPN BJT. BJT stands for bipolar junction transistor. So this N-type, P-type, and N-type LEDs are called the collector, base, and emitter. Here we have the PNP type, and this is called collector also, base, and emitter. You will notice the arrow is pointing outward in the NPN, and the arrowhead here is pointing inward in the PNP symbol. Now, let's look at it again. This is an NPN BJT, or the NPN bipolar junction transistor. This is the schematic symbol, completely labeled with C, B, and E, or N-type, P-type, and N-type. And this is the NPN BJT construction. This is the N-type, P-type, and N-type with collector, base, and emitter. And this one is the diode equivalent. On the other hand, for our PNP BJT, this is the schematic symbol. Still the same, we have the collector, base, and emitter. Take note that the emitter contains the arrow, and this is the construction of the NPN BJT. And we have the P-type, N-type, and P-type block here, which has also a label of collector, base, and emitter. Here we have the PNP BJT construction also as symbolized by a diode. This is a back-to-back diode with its cathode connected together. So this is the symbol, this is the construction, and this is the diode equivalent. Now let's move on to the next page. Here, this is the summary of some formulas that we need to know in making sure that our NPN transistor or BJT is connected in the correct way to make it as an amplifier. First of all, you have to consider the base to be connected on the positive side of the VBB, because this is P-type and this is positive. This will be in forward bias. If you are using PNP, then just in case that you're using PNP, so this is N-type, you should not connect it to positive. You must connect it to the negative if it is N-type base. Now, on the collector side, you will see that this is N-type connected to positive. So this is N-type, which means that majority of the charge carriers are electrons. So if you connected it to a positive source, then it will be in reverse bias. And precisely that's what we mean. We need to connect the base to the positive and the collector to the positive, so that we will have forward bias on the left side or the input side, and we will make it reverse biased in the output side here on the right. Now, the VBB stands for the base supply voltage, or base bias voltage source, and the VCC stands for collector supply voltage or collector bias voltage source. The voltage between the B and the E is called VBE. This is a voltage between base and emitter, and the VBE is approximately equal to 0.7. This is for the silicon transistor. Now on this side we have the collector and the emitter voltage, we call it VCE, and we have also a voltage between the base and the collector, we can call it VCB or VBC, and the voltage on the input side, if you will apply the Kirchhoff's voltage law, is that the source voltage is equal to the load voltages sum. So we will have it like VBB is equal to the voltage RB plus the voltage BE. In other words, the voltage VBB is equal to the sum of VRB and VBE. Now, if we want to calculate for VRB, for example, then we can subtract VBB minus VBE. And we all know that VRB can be calculated by multiplying the IB multiplied by or to RB. So if you separate the IB, just in case you want to calculate IB, then we have VBB minus VBE over RB. This is very important to know. This will be the basic calculation for the current on the base. IB is equals to VBB minus VBE over RB. Now, on the case of VCB or VBC, we can calculate it by subtracting VCE minus VBE. Or you can say VB minus VC also, if you want to calculate for VBC or VCB. Now, for the BE, this is again forward biased, and the BC must be reversed bias. And we call this circuit as forward reverse bias of NPN bipolar junction transistor. Now take note that the current E or IE is equal to IB plus IC. So the IE, which is coming out from the transistor, is equal to the sum of the IB coming into the transistor and IC coming into the transistor, perfectly showing you the Kirchhoff's current law, which says that the output current is equal to the input currents. So it's like here that the input currents, IB and IC, the sum of them will become the output current IE. So that's why we have IE equals to IB plus IC. Now previously we have discussed that the beta is equal to the ratio of the IC over IB. And if you want to calculate for the alpha, then that will be IC over IE. So this is the calculation of beta and alpha, IE, IB, VCB or VBC, and the VBE is constant, 0.7. Now, if you want to calculate for the VCE, you may subtract VCC minus the VRC. But VRC by Ohm's law is equal to I multiplied by R. That's why here we have VCE is equal to VCC minus ICRC. So take note that the arrow of the emitter points in the direction of our conventional current. When we say conventional current, it's like positive to negative. Now the symbol again for NPN, don't forget, is this. We have the arrow pointing outward, and if the arrow is pointing inward, then that will be called PNP. Now moving on, let's go back again with our formula. So we have discussed the formula for VCB or VBE, VBC, and then the beta and the alpha and the IE and the VBE. And the VCE also here, if you want to calculate, I said VCC minus the VRC, but VRC by Ohm's law is ICRC. Now the IB, as I have said, is equal to VBB minus VBE over RB, and the VBE is 0.7 volts for our silicon transistor. Just in case that it's mentioned in one problem that it is germanium, then you have to use minus 0.3 volts. So if you want to calculate the IC, you may use beta multiplied by IB. And again, the IE is equal to IB plus IC. All right. Now let's move on with the collector characteristic curves. This is a set of collector characteristic curves that can be generated to show how the collector current IC changes or varies with the VCE and the collector to emitter voltage for given values of our IB. That's the definition of a collector characteristic curves. Again, this is a group of collector characteristic curves that we can produce just to show how IC changes with VCE. That's why we will have the VCE on the x-axis and the IC on the y-axis. And we have to make sure that our collector to emitter voltage or VCE is represented on the x-axis and the IC on the y-axis. And we make sure that the IB is given. We can change the IB and then we will be drawing the characteristic curves. As you can see here, this is one example. The IC is on the y-axis and the VCE is in the x-axis. And if we increase the VCE, of course, the IC will increase here from point A to point B. So while it's increasing, then this is what we call as the ohmic region. And from here, from point B up to letter C, this is what we call as the saturation region. This is the region where we can consider the base of the IC will become constant. And if you keep continuing increasing the VCE, it may come a point that the IC will increase again. And if that happens, then it means that we already reached the breakdown region. Now, between the saturation region, letter B, and letter C, this is the one in the middle. This is what we call as the active region. And if your IC becomes 0, then you will be reaching the cut-off region here at the bottom. So going back here, let's look at the circuit. So this is the VBB, which we can change to vary the IB so that we will get the collector characteristic curves. And the VCC also is on the right side so that we can also change the VCE. So we will assume that the VBB is set to produce IB, and the VCC we can make it equal to 0 volt. And the BE junction and the BC junction will be forward biased because the base is 0.7 volts, while E and C are at 0 volts. So E and C will be at 0 volts if you do this situation. Now, if the IC equals 0 and both junction BE and BC are forward bias, of course. So the transistor is in the saturation region of its operation when you have that situation. Now here, the collector current in the saturation has reached a maximum and is independent of the base current. It is not affected anymore by the IB when you reach the saturation region. So in other words, the IC will no longer increase or decrease based on the IB. It has no more effect because it's already saturated. And even if you still increase the IC in your amplifier, then it will not move to a higher value because we have reached the IC saturation. Now, as the VCC increase in the right side, of course, the voltage in the CE will increase because the current IC will increase. So the bigger the VCC, the bigger will be your IC, and so that the bigger will be your VCE. Now, when the VCE is more than 0.7 volts, the BC junction will become reverse biased and the BJT will become active, or it will go to active region, which is between point B and point C. And here, if you increase the VCC and the VCE, and this approximately reach more than zero point 0.7, the IC will become constant for a given value of IB as VCE continues to increase. Now, when the IB is equal to 0, the BJT will be equal to the cutoff region. So, this is, although there's a very small leakage IC, of course, but when the IB equals 0, of course, the IC will be equal to 0, or there's a small leakage IC, but this is still in the cutoff or non-conducting state. But when VCE reaches a sufficiently high voltage, the reverse biased BC junction will be going into a breakdown region, and the IC will be increasing very fast. It's like you have broken your transistor. Now, how do we draw the DC load line? The DC load line is drawn by making the y-axis as your IC, expressed in milliamperes here, and the x-axis as VCE. Now, all you have to do is to just take the VCC value, which is 12 volts, find it on the x-axis, and put a point. And then you have to calculate for your IC saturation by simply dividing the VCC divided by the RC. Again, you can get the IC saturation by dividing BCC over RC. And when you get the answer, for example, here we have 12 volts divided by 1 kilo ohm, then we got a value of 12 milliampere, and that will be placed here in the IC. And take a point. And then just draw a straight line from the 12 milliampere down to the 12 volts, and there you go. You will have your DC load line. Now, if you want to put your Q point or the operating point, then you have to consider calculating IC first and then calculating VCE, and whatever will be your answer for the IC and for the VCE, then that will be your Q point. Now, let's see another example here. This is when VBB equals 0, of course, the IB will be equal to 0. When there's no voltage source on the input side, the VBB is 0. Of course, the current IB will also be 0. Therefore, the IC will be equal also to 0, and the VCE will be equal to 12 volts. This is the maximum. And the point where IC, which is equal to 0, and the VCE equals 12 volts can be found in the characteristic curve. And this is the first extreme point. We call it cutoff. That's why here you will see that in the cutoff, the IC equals to 0 milliampere, and our VCE, of course, will be automatically be 12 volts. Now, when the VBB is increased, not 0, of course, there will be current IB, and it will increase, and it will keep increasing as long as you increase the VBB. Again, if you increase the VBB, the IB will also increase. But there will be a point where the IC will be so much that the VRC will be equal to VCC, or approximately equal, and the VCE will be equal to 0. What we mean is, if you keep increasing the VBB, there will come a point that your IC will no longer increase. And when that happens, when you increase IB until the VCE becomes 0 and the IC will be at its maximum, this is what we call as IC saturation. And the IC cannot go any bigger than this IC saturation. It means that no matter what you do, the IC will still be the same, unless you have broken the transistor or you have reached the breakdown region. Now, the IC, to calculate for the saturation, just divide VCC over RC, just like what we did here. Although I was not able to put here IC sat, but I refer to this as the saturation IC. Now, the VRC will be equal to VCC, and therefore, by Ohm's law, IC multiplied by RC. If you get the value of VCC here, that's equal to ICRC. So our limiting factor here is that the VCE can get any smaller. It cannot get any more smaller than 0 volts. Because once it becomes 0 volts, It's not gonna get any lower than that, and the IC will be at its maximum. Now, again, let's look back on the forward reverse bias of a PNP BJT. This time, PNP, I mean, not NPN. So if it is a PNP BJT, still, you have to make the input circuit here on the left side as forward biased. You will see that the negative of my VBB is connected to the base this time because I'm using a PNP transistor. But before, we were using NPN, so if it is NPN, this must be positive so that it will be forward bias. Again, P-type to positive, forward bias. N-type to negative, that's still forward bias. Therefore, either you use NPN or whether you use NPN or PNP, we can still make it as an amplifier. So on the collector, which is P-type, it must be connected to negative so that it will be in a reverse bias. That's why this circuit, although we are using PNP BJT, this is still considered as an amplifier because the base emitter junction is forward biased and the base collector junction is reverse biased. Now, for the transfer characteristics and parameters, as I have mentioned, the calculation for beta is equal to IC over IB, and a small change in the IB will result to a large change in the IC. You can also represent the IB as HFE, and this is referred to hybrid parameters. Now, let's say we want to determine the beta of a transistor, and we are given IB 50 microampere and IC 3.65 milliampere. It's so easy. Just divide the IC by the IB, but be careful with the units, like the 3.65 is in milliampere, so you have to express it as 10 to the minus 3, while the 50 microamperes is expressed as 10 to the minus 6. And we will get the answer of 73 without any unit. So this is for beta. Now for alpha, this is the relationship of current change or collector to emitter, where the delta current will be from between the collector to emitter is called the alpha. And the alpha is always less than 1. So the normal values for this is 0.95 up to 0.99 plus, but it will never reach 1. It must always be less than 1. Example, we are given here IB 50 microamperes and IC 3.65 milliamperes. Again, we divide the IC this time by IE, and we will be getting 0.999. Now that you have your, let's say you don't know your IE, because here we were given IB and IC. So we first need to add the IB plus IC before you can calculate for the alpha. Again, in the question here, the IB is given and the IC, so you add the two, but be careful with the unit because this is microampere and this is milliampere, so you cannot directly add the values of these two. So you have to consider multiplying it to 10 to the power of minus 6 and 10 to the power of minus 3. Now, the BJT characteristics, once again, of an NPN BJT CE configuration is like this. We have the IB on the y-axis. You may express it as microamperes. And then in the VBE, this is the x-axis. Then you just draw a curve similar to the curve on the forward biased diode. And we may take 2 points on one curve. And let's say this point is IB2 and this point is IB1. We can subtract the values of these two IBs, and that will be the delta IB. On the other hand, this point downward will be called, for example, as VBE2, and this point downward is VBE1. If you subtract this, you will get the delta VBE. So that's how to draw the input characteristic of an NPN BJT common emitter configuration. But take note that this is using a constant voltage CE of 2 volts. Now, if you change your VCE, of course, the curve will change a little, and this is represented by the second curve here, which uses 10 volts, and this one is using 20 volts. Now, again, this is the BJT amplifier, common emitter configuration, NPN transistor. We have here the VBB, and the point between the B and the ground, we call it VB. Between B and E, we call it VBE. Between the VCC and the ground, of course, we call it VCC. The voltage on the RC is VRC. The voltage on the C is VCE. The voltage between B and C is VBC, and the voltage on the resistor RB is called VRB. Again, the voltages on the resistors can be calculated by multiplying each current. Like here, this is VRB, so the current here is IB. You can multiply it to RB and you will get VRB. On the other hand, for VRC, we can multiply IC uh, to RC so that we can get VRC. Again, this is the NPN BJT common emitter mode. Now, just to give you again the definition of input characteristic, it describes any changes that happen in the input current because of the variation or changes in the input voltage. But make sure that we keep the output voltage as constant. This refers to the IC, or which is controlled by VCE. It's as good as making sure that the VCE is constant. Now, the output characteristic, on the other hand, is a graph of the output current on one axis and output voltage on another. Again, at a constant, this time, input current, not the constant uh, input voltage. Now, this is the output characteristic of the NPN BJT common emitter configuration. This time on the y-axis we have the IC expressed in milliamperes, and on the base we have the on the x-axis we have the VCE. And the curve is not the same because the IC is increasing here as you increase the VCE, but there will come a point that it will reach this knee point, which we call as the start of the saturation region, and more or less the current will be approximately the same at this point, and this is called the saturation region. Now, while the current is still increasing, that's called ohmic region, and the one here down here in the along the x-axis, we call this as the cut-off region, where the IB is approximately equal to 0. And in between the saturation region and the cutoff region, this is what we call as the active region. So this is the output characteristic of the uh, NPN BJT transistor. But I'm sorry for the spelling here. This is characteristic. We missed writing the letter A and the letter C. So there's another curve which we call as the transfer characteristic curve, and this is just drawn between IC and IB. So we just make the y-axis IC and the x-axis IB, and then we plot the value of the IC and the IB with a particular value of VCE. The IB will be increased in different or suitable steps, and the IC will be written down for each IB that we increase. Now, to calculate the current gain, we just divide IC to the corresponding change in IB at a constant VCE. And this current gain is represented, as I have said before, by beta, IC divided by IB. But how will we get the change in IC and the change in IB? All you have to do is to take any point on the line or along the line, and this point, you will just subtract the IC here, IC2, with the point here, which is IC1, and there you go, you will get your delta IC. And the point down from this point downwards will be called IB2, for example, and the point here downwards will be IB1. If you subtract IB2 minus IB1, this will be the delta IB. Again, you may take any 2 points along this line. And then after that, you divide your answer by IC divided by the IB. And that's the transfer characteristic curve. I hope you subscribe to this video, and we will continue the next discussion on our next video. Please subscribe, like, and share towards our goal to reach 1,000 subscribers. Thank you so much. Okay, let us say that we will be taking or finding the DC values like IB, IC, VCE, VB, VC, VE, VBC, IC saturation, Q point, and we want to draw the DC load line. Look at the circuit here. We have the VBB equals to 5 volts, RB equals to 400 kilo ohms, RC equals to 220 ohms, VCC equals to 12 volts, and we have beta of 80. So the first thing you will do is to calculate for IB. Now to do that, we have to use the formula VBB minus VBE over RB, and then we subtract 5 minus 0.7 volts divided by 400 kilo ohms. And we have to be careful with the units. This will be 4.3 volts divided by 400 kilo ohms. We all know that when you divide volts by kilo ohms, the answer will be in milliamperes. So I directly put here 0.01075 milliamperes. This will be our IB. But you can move the decimal point to the right 3 times, 1, 2, and 3, and you will put the point or decimal point between 0 and 7. Thereby, we will be getting 10.75 microamperes. But it doesn't matter whether you write 10.75 microamperes or 0.01075 milliampere because it's the same. Then we calculate for the IC, which will be equal to beta multiplied by IB, and that will be 80, which is given, and the IB that we have previously calculated in milliamperes, and therefore the answer here is 0.86, also expressed in milliamperes. Now, if you multiply 80 by the microampere, then your answer for IC will be microamperes. So we got IC equals to 0.86 milliampere. Thirdly, we will calculate for the current or the voltage VCE. So we just subtract ICRC, which is the voltage on the resistor RC, again by Ohm's law. VRC, or the voltage on the RC, is equal to IR. That's why we can multiply the IC that we have calculated to the RC to be able to get the VRC. Now, when you subtract VRC from VCC, you will get VCE. Again, going back to our circuit, VCC is equal to VRC plus VCE. VCC equals VRC plus VCE. But if you want to get VRC, you can subtract VCC minus VCE. VCC minus VCE will be your VRC. Now, if you want to get VCE, you can subtract VCC minus VRC. If you don't know VRC, use Ohm's law, multiply the current IC by RC. That's why we have here VCC minus ICRC, and we got an answer of 11.828 volts. Thirdly, we will calculate for the base voltage, VBE. Base voltage will be from the base down to the ground. So you put the positive of your DMM to the base and the negative on the ground, and that's how to measure the VB. But for calculation purposes, we can just make it equal to the value of BBE. So it is approximately more or less equal to 0.7 volts using the silicon transistor. If it is germanium, then it's 0.3. Now the VC is from the collector up to the emitter, up to the ground, and because the collector down to the ground is also taking the voltage between the VCE, and we don't have any resistor, then the VC will be equal to VCE. Again, if you did not understand that, if I take the VC from here up to the ground, then it's the same as taking VCE because there's no resistor here. So VC is equal to VCE. Then we can have the VE equal to 0 volts because there's no resistor on the emitter. And for VBC, just subtract VB minus VC, and you will be getting 0.7 volts minus the answer here on number 5 11.828, and we got a negative value of 11.128 volts. This negative, never mind it. It means only that the base collector junction is in reverse bias. Therefore, if you got positive here, then your base collector is not connected in reverse bias. It's most probably connected in forward bias. And if that happens, then the transistor will not be in reverse bias. It will break the rule of the amplifier where the BC junction must be reverse bias. So never mind the negative here. It just means that the BC junction is in reverse bias. Now on number 8, we calculated for IC saturation using VCC minus VCE over RC, but the VCE saturation, we assume that it's 0, so it will be VCC over RC, so 12 volts divided by 220 ohms, we get 54.5 milliamperes. In ampere, it's 0.0545. Now, if the VCE saturation is given, then you have to subtract whatever given VCE saturation is from VCC. But if it is not given in the problem, then you have to make it 0. Now, after taking the IC saturation, just plot it on the y-axis IC and also plot the 12 volts VCC here. And from this point of IC saturation down to the point of VCC here along the VCE, then you can draw a line, and that will be called as your DC load line. Now here between the two, we will put Q point, but the values for the IC and the VCE must be equal to the calculated IC here, which is taken from beta IB 0.86, and the VCE that we calculated by subtracting IC/RC from VCC, where we get 11.828. Again, the IC is 0.86 here, and the VCE here is 11.828. Therefore, we must put here the ICQ as 0.86 and the VCEQ as 11.828. That's how to get the Q point. And this is called now the ICQ and the VCEQ, which comes from the calculated value of IC and VCE. There you go. You have the Q point and you also have the DC load line. I hope you like this video, and you will subscribe and share it towards our goal of reaching 1,000 subscribers. Please like the video and share it to your friends so that they will also learn about NPN BJT amplifier in a common emitter configuration. Thank you so much.